All right, as we get started today, we're going to begin with ACT prep. So if you're watching on YouTube, you'll find this in the description of the video. Take about 12 minutes to work on these 12 problems. Once you're finished, go ahead and resume the video. But for now, go ahead and pause and work on it, and you can resume. All right, let's go ahead and take a look at the ACT prep and see how you did. And number 37, it says that A, B, C, and D are collinear. That just means, yes, that really is a straight line across the bottom. And then FC is parallel to ED. So that's an important fact. They look parallel. They really are. It also says that BE is perpendicular to ED. And you see that perpendicular notation. It says the measures of FAB and EBA are as marked. They've got a couple of angles, 63 degrees there at A and 147 there at B. It says, what's the measure of angle FCB? What did you get for your answer, Quentin? B, 57 degrees. How many also had 57? Let's take a look at this very quickly. You know that this line and this line are parallel. You also know that these two lines are perpendicular. Therefore, these two lines are also perpendicular, aren't they? If so, then this right here between B and C has to be a little right triangle. And we know that there's 147 degrees out here, which leaves 33 degrees in here. But it asks, what's the measure of angle FCB? Well, we know that the two acute angles of any right triangle are complementary. And when you subtract the 33 from the 90, you'll get 57 degrees. Does that make sense now? So just a lot of geometry in there. Number 38 is something that you haven't learned yet. We briefly referenced this in Algebra 2, this idea of quadratic equations, and we said that a most base quadratic with one squared variable gives you a parabola. But I said if you were to square both variables, you could get a circle. If you squared both variables and you changed the number in front of one of them, you would get a squished circle, or a squished circle this way, called an ellipse. And then I said if you were to divide the variables or subtract the squares, you'd get some weird hyperbolic shape and stuff like that. But coming back here, something you might not remember is that anytime you have an x squared plus a y squared, just straight up plain old x squared plus plain old y squared, this beginning of an equation is always going to be a circle. Well, that right there narrows it down to either class J or K, right? So we know it's either J or K since it says which of the following is the equation of the circle. You know it's one of these two. Now, the question is, what number is it? Is it the one with the 5 or the 25? Well, if the center's at the origin and it goes through the point 3, 4, then you know this line is 4, this line is 3, the hypotenuse has to be 5. But the form for the circle is x squared plus y squared equals r squared. I would write that on this paper and memorize it. You will almost definitely see some circle problem on your ACT test. And if you know this, that x squared plus y squared equals r squared is your equation for a circle, you're good enough with trigonometry to figure out the radius. You just didn't know that the radius has to be squared after the equal sign. And didn't know yet that it's the x squared y squared unless you paid really good attention and have a really good memory because it wasn't a point of emphasis. It's something we'll talk about later on in the year when we talk about conic sections and things like that. But for now, this should get you through the ACT test coming up in a month or two. Does that make sense? So memorize that fact. So if the circle had a radius of 2, what would the equation be? Assuming it's centered at the origin like this one was. X squared plus y squared equals 4, right? If it were a radius of 12, it would be x squared plus y squared equals 144. Make sense? So just a little something to tuck away there in case you see that circle. Now again, that assumes it's centered at the origin, but again, we'll get into all kinds of interesting stuff we can do with circles. Put it away, Glenn, or it becomes mine. Last call. Put it in the pocket. We'll talk about all of that later on in the year, but again, for now, hopefully that'll get you through the ACT. Everything else on here we should be good with. Number 39 says, which of the following expressions has an even integer value for all integers A and C? What did you put for this one, Jamie?
H.
Ethan?
F.
f. Think back to what we said in Algebra 1 and Algebra 2. We said if you wanted to represent, quote, any even number, you'd represent it 2x, correct? That guarantees evenness. Now on letter, you said letter H, Jamie? H, 2a guarantees that that portion would be even, but there's no guarantee that the c comes out even. And if you had even plus odd, you'll come up with an odd. So we have to guarantee it. Well, you realize I said 2x guarantees even. 4x would also be even, right? As would 6x or 8x or 10. Really, as long as the coefficient's even, we're good. And that's what we see in letter F. 8a has to be even, regardless of what letter A is. And then A and C, I don't care what they get when they multiply. As soon as you multiply that by 2, you get another even. And even plus even always gives even. So that's why letter F is our answer. Number 40. Neighborhood recreation program serves 280 children who are either 11 or 12. The sum of the children's ages is 32, 38 years. How many 11-year-old children does the program serve? There's a lot of different ways you could approach it. I would go system of equations here. Curious what you got for your answer. Let's see. Quentin, I called you the first one, right? Jamie, all right, let's go to Ethan.
D.
Not D.
I put A.
Is not A.
Oh, not A, I put E.
Not E. Oh, just kidding. I put. Go ahead, Glenn. Quentin.
C.
We're guessing, aren't we?
Yeah.
B. All right. Let's review how to solve this. And we've seen a few of these systems of equations already leading up to this. Let's take a look at another system of equations here. There are 280 kids, right? Some of them are 11, some of them are 12. Since I don't know how many are 11, class, we could call that number X. So X is the 11-year-olds. And let's call the number of 12-year-olds
B.
What?
B.
B. All right. So we know that there's 280 kids. Some are 11, some are 12, but there's 280 total. Class, the equation should be?
3, 2, 11, X.
How about just X plus B equals 280? Right? 280 kids. Some of them 11, some of them 12, 280 kids. Now, if we took the sum of the ages of all the 11-year-olds, since every one of them is 11, what could we get for all of their ages together? 11x, right? 11 times the number of 11-year-olds gives you the sum of the ages of all the 11-year-olds. How would we represent all the ages of the 12-year-olds put together? 12b. And if we add the sum of all the years here plus the sum of all the years here, that gives us a total number of years of
3,238.
And that's the system of equations we should have set up. I would write that system down next to problem 40 on your paper. I'd write that problem down. Now that we've addressed it, do you remember going over that kind of thing before? We actually had a problem last year in geometry. It was a practice exercise, and there was this guy, a farmer guy. Remember, he had chickens and cows? And he said he has this many heads and this many legs on his farm. Do you remember that one? I just thought it was kind of weird, but we took, well, every animal just has one head, right? So we said chickens plus cows equals whatever. It was like 40 heads. But every chicken has how many legs? So 2 legs per chicken, and then how many legs does every cow have? 4. So 4 times the number of cows equals, I think it was like 120 legs on the farm, something like that. And we made our system this way. We've got 280 kids, some of them 11, some of them 12. But 11 years times the number of 11-year-olds plus 12 years times the number of 12-year-olds equals all the years put together. Does that make sense? To solve a system of equations like this, again, we want the 11-year-olds, right? So strategically, I don't want to get rid of x. I want to get rid of b. We'd multiply the top equation through by 12. So you get 12x, 12b, and somewhere on the calculator, 12 times 2,080, or 280, excuse me. 12 times 280? 3360. All right, we'll change the signs across the bottom because that's where the smaller numbers are. Cancel the 12b's, and that's where we get x equals 2 to 122, which was letter B. Questions on this now? All right, use systems of equations. As you've caught on, we've done 40 problems now, and I'd say we probably have like 3 or 4 systems of equations. It's almost 1 out of every 10 to 12 problems has involved a system. So making mental notes as we prepare for the ACT, we better be good to go on systems of equations. Number 41, it comes back to graphing parabolas back in Algebra 2. And remember we said a parabola has an answer everywhere it crosses the x-axis. So we get an answer here called the roots of the parabola, the root of the equation. Well, the easiest way to solve this is instead of setting it equal to y, what do we usually set quadratics equal to?
0.
0, because we don't usually graph them, do we? Because we're too lazy, right? I'm too lazy to graph this one. I'm going to say 0 equals x squared minus 4x plus 4. And then after we set it equal to 0, then we would factor, right? Backwards FOIL.
Where's the y? Where's the y going?
We changed it to a 0 because we didn't want to graph it. The only reason you need a y and an x is to graph. But we're not going to graph it because we're too lazy. So we replace it with a 0. And which y equals 0 all along here, which is why we could replace y with 0, just technically, going back for review. X and x, sines, and split up the 4.
2.
And when we say each of these equal to 0, what do we get for x?
Positive 2.
Positive 2 and
Positive 2.
positive 2. In other words, this parabola only comes down and touches at positive 2. It doesn't intersect twice. We get what are called two coincident real roots. Vague flashback to learning this right before COVID hit a couple of years ago. It was right before coronavirus, right at the end of that third quarter where we were working with these.
I learned this in mid-August.
Well, yeah, it's true. You learned it a little bit later than the rest of them did. But anyway, the only acceptable answer is positive 2. So letter E should have been our answer. Letter E, our answer. Questions on that first page. Do we understand it now? All right, we're going to be able to do this on the ACT. We understand it well enough that with the notes we've written down, we're going to be able to go back and review and refresh, and we'll be ready for the ACT instead of floored by it. I hope. All right, let's take a look at the next one. Read it for me because my voice is starting to go all the way through number 42. Chris. Tahir, I don't know how you pronounce his name.
Tahir has decided to create a triangular flower bed border. He plans to use 3 pieces of rectangular lumber with lengths 4, 5, and 6 feet, shown in the figure below. Points A, B, and C are located at the corners of the flower bed. Tahir plans to cut 3 pieces of lumber for the flower bed border from a single piece of lumber. Each cut takes an 1/8 of an inch off the length of the piece of lumber. Among the following lengths and inches of pieces of lumber, which is the shortest piece that can be used to cut down pieces of the flower bed border. That's the flower bed border.
All right. So, well, if one piece is 4 feet, one piece is 5 feet, the other piece is 6 feet, class, how many feet does he need? 15 feet, right? But a foot has how many inches? 12. So all we have to do is multiply. Larger to smaller, multiply. This is junior high level stuff. And how many inches are the pieces of lumber going to need to be? 180. But every time he cuts, how many have cut wood before? You know the sawdust, you lose a little bit of length. He's going to lose 1/8 of an inch every time he cuts. So if he has exactly 180 to start with, and he's going to make 2 cuts, right? When he cuts the first piece, cuts the next, well, assuming he's got longer than that, cuts one piece, cuts the next piece, cuts the other piece just exactly, I guess that's technically 3 cuts, he's going to lose 3/8 of an inch. So he would need 180 and 3/8, right? Well, that's not an option. So what answer should we go with? D, 181, which gives him 5/8 of an inch little piece that he can throw in the fireplace later. All right, questions? How many had the D? You thought it through properly. All right, does it make sense now if you didn't? All right, number 43. This is interesting. It says the measure of angle ABC in the figure is x degrees. You see that on the picture. Which of the following is an expression for beta degrees? How does beta compare to angle x? Chris?
I put 2x.
It's not twice as big. Quentin?
Okay.
180 minus x? How did you get that?
Because it's a complementary.
It's complementary?
Because the 2 angles together would make 180 degrees.
How did you get x and b? Because don't they look like vertical angles, class? Kind of, but x or beta looks bigger, doesn't it? Why? Because these aren't just straight lines. If these were straight lines intersecting somehow, then x degrees and x degrees would be the same. But they're not just lines connecting, they're pieces of lumber that have in them right angles, correct? And if we were to go all the way around, class, that would be how many degrees? 360. But 180 is already spoken for, correct? In the 290s. So that leaves 180 degrees between x and beta. So, how do I find beta? 180 minus x degrees. You're exactly right, Quentin. Letter J is our answer. How many got J like Quentin did? All right, question on it now. Does it make sense now? And again, on the surface, you're almost like, oh, well, duh, they're vertical angles. It's got to be X also. And like, whoa, wait. We have right angles in the corners of the boards. That's where it takes a little bit more thought. So if you put F, I understand the thought behind it. Number 44, read that one, it's long. Ethan?
After arranging the flower bed to here, besides that the flower bed would look more attractive if one of the angles in the triangle were a right angle. It decides to place the right angle at vertex A and the lengths, and to leave the lengths of AB and AC as 4 feet and 5 feet respectively. To the nearest 0.1 foot, how long of a piece of lumber would you need to replace the 6-foot piece represented by PC?
All right, well, when you look at the picture, look at angle A. It almost looks like a right angle anyway, correct? If it were a right angle, 6 wouldn't be big enough to be the hypotenuse, would it? How would I find the proper length for the hypotenuse, class? Pythagorean Theorem, right? Just use the Pythagorean Theorem. If you have a leg of 4 and a leg of 5, how long does the hypotenuse board need to be? And we should get anyone? Uh-oh. 6.4 when we round to the nearest tenth of a foot. By the way, you knew it had to be bigger than A, B, and C, right?
Yeah.
Because 6 is what you had before, okay? And 6 is going to be too small, presumably, so it's either D or E, and letter D is the correct choice.
I looked at the picture and kind of like, did it kind of try to do it with my hands.
Right,
And
yeah.
I got 6.4.
All right, questions on that? All right, turn the page. Back to junior high pre-algebra. Geometry stuff. Read that for us if you would, Jamie.
The geometric figure shown below consists of a square and 4 semicircles. The diameters of the semicircles are the size of the square, and each diameter is 10 centimeters long. Which of the following is the closest approximation of the total area in square centimeters of this geometric figure?
All right, so we know, first of all, if the square is 10 by 10 by 10 by 10, class, how big is the square?
20.
That's perimeter. We're talking area. Bless you.
100.
I'm sorry?
100.
100 centimeters squared. That's just in the square, though, right? And then we've got 1 semicircle, 2 semicircle, 3 semicircle, 4 semicircle, right? 4 semicircles is always going to equal what?
2 circles.
2 circles, right? And every time you find the area of a circle, we would use the formula A equals pi r squared. But we have 2 circles, so the total area of the semicircles is going to be 2 pi r squared. Make sense? So 2 times approximately 3 times a radius of, well, it gives a diameter of 10, right? If this line is 10, then the radius is 5 squared, 25. So 2 times 25, 50 times 3, 150. That's 150 total from these, plus the 100. Now again, this was an approximate, right? It's going to be a little bigger than 150, but it's just round numbers. So if we really rounded it off, what would we come to? 250, right? Which of those numbers is closest to 250? H, 260. It's actually 257-ish if you round to the whole number, but hey, we're just rounding something close. So 260 is a great guess when you're in a hurry and don't want to pull out the calculator. How many got H? 260. All right, good job, gentlemen. Questions? Does it make sense now? All right. Number 46, we better have gotten this one, all right? Because this is now, right? This is trigonometry. Oh, okay. Read it for us, Quentin.
Which of the following expressions is closer approximation to the height H in feet of the roof truss shown below?
All right, so we've got this roof truss. Of course, there's all kinds of little zigzaggy lines, but all we really want to know, class, is H. So ignore the other joists and supports, right? And we've got a 20-degree angle here, and the entire length of the roof beam is 30 feet, correct? But assuming the height to be perpendicular to the cross beam, how long is this half of the cross beam? 15 feet. Now I ask the question, why would I want to cut it in half? Because in cutting it in half, class, instead of a great big isosceles triangle, I get a smaller right triangle. And since everything in here is trig ratios, I know I've got to have a right triangle. Does that make sense? So I know I need to cut it in half. Because I see trig functions. Trig functions need right triangles. Cutting it in half gives me a right triangle. So question, with respect to the 20, h is the opposite and 15 is the adjacent. Opposite, adjacent,
And
tangent. We know that the tangent of any angle, in this case 20 degrees, is equal to the opposite h over the adjacent 15 feet. But it says, what's the height of h? How would I find h, class?
multiply, cross multiply.
Cross multiply it. 15 times the tangent of 20, which is letter A. 15 times the tangent of 20. Does it make sense now? See the right triangle is the key. So anytime there's trig ratios involved, see the right triangle and apply accordingly. Number 47, back to a little bit of geometry class here and a little, well, really all geometry, I guess. Read that one for us, Chris.
Quadrilateral ABCD is drawn on standard XY coordinate plane as shown below. Points E and F on AB. Point G is the center of the rectangle BCE at how many coordinates units long as AG?
All right, AG. So we see that there's this, that says it's a quadrilateral. It doesn't actually say there are any parallels, does it? Oh, it says there's a rectangle. Do you see that? BFEC forms a rectangle, which means these two lines are parallel, class, which means we do have a, well, more specifically a trapezoid, right? The fact that a rectangle could be formed in here tells me there is technically a trapezoid. That's good to know. So we've got 0, 0, we've got 12, 0, we've got 15, 0, we've got 6, 4. Now question, y value 0, y value 0, y value 0, right? So what's the y value here?
Or 6, 0.
0. And the x value, since it's a rectangle, has to be straight up and down. It's got an x value of 6, right? So this is apparently the point 6, 0. What's this point up here? 12, 4, right? So just figuring out some of those. And then it says that G is the very center. Well, 6, 0, 12, 0. Right below this would be what point, class?
9, 0.
9, 0, correct? And right up here would be what point?
9, 4.
9, 4. Right in between them would be what point?
9, 2.
9, 2. You follow? Now, how would I find the length of that line? How would I find the length of that line?
Triangle.
Pythagorean Theorem, how long is this line, class?
15.
Oh, this line,
9,
9, right? How long is this
0.
line? 2. If we got a line of 2 and a line of 9, how do I find the hypotenuse? Pythagorean Theorem, I get the square root of the square root of 85. And letter H should have been our answer. Letter H. Does that make sense now? A lot of just picturing and lining it up, a lot of geometry ideas here, and just, I guess a trig idea, though we did talk about Pythagorean Theorem in geometry anyway. And then number 48, kind of an intuitive problem here. It says for all non-zero real numbers, because again, you can't have denominators of 0, right? So y and t definitely cannot be 0, but we also can't get a value of 0, so x and p aren't 0 either. Which of the following expressions is equivalent to t? Don't make this too hard. When it says is equivalent to t, you know what it's asking? What is t equal? In other words, get t by itself. And to do that, since it's in a denominator class, I'll want to, I could. I was just going to alternate. Put the 2t here and the x here. Now how do I get the t by itself?
Times the y.
Times the y, divide by 2. And there's my answer, 3py over 2x. It is letter K. Letter K. Questions on that? It's a little bit of literal equations. So actually what we were just doing in Algebra 1 today, in fact. Questions on this? All right. Seemed like we struggled a little bit more with this. Now, 2 thoughts to take away. Number 1 is this. If you're feeling like, man, this ACT stuff's hard, I gave you a set of SAT stuff to work on. Go through that. We'll work on that a little bit more tomorrow, I think, as well. And you get a chance to see, which do I think is easier? right? Maybe you feel like the SAT is easier for you. Maybe you feel like the ACT, but compare them and decide which test to take based on that. Also, save the stuff, right? Don't throw it away, save it with the others. Make sure you've got some notes for yourself, so that way you can go back, review over these. Again, are these going to be the problems on the ACT? No. I'd be shocked if even one of these was on there. But similar problems, the same way of thinking, the same kinds of things. This is great review for. Any questions before we put it away and get back to pre-cal? All right, set it aside. Take your homework handouts out. Homework handouts out. And hold it up so I can see the front side first of all, where the big chart was. All you had to do was finish filling in the quadrants 3 and 4. Good. Good, good. And again, the big thing with filling in the chart wasn't doing a whole lot of math, right? The biggest thing was get quadrant 1, and then we didn't do any more math the rest of the way, did we? All we did was figure out which row to copy, and then which signs to make, or which functions to make negative, right? Where do we put negatives, where do we put positives? And the point of all of that, just to give you practice seeing the patterns. But on the back side, we weren't using the chart. So flip it over now. And let's take a look at the back side of the page. As we find exact values of trig functions, of special angles outside the first quadrant, the first thing you got to know is what quadrant are we in, Chris?
First quadrant. No.
135.
Second.
Quadrant 2. Once we've identified the quadrant, we identify the reference angle. In quadrant 2, measured from 180. Quadrant 3, measured from 180. Quadrant 4, measured from 360. Here, reference angle is 45 degrees. And then we go to our special triangles. What is the secant of 45 degrees?
1 over square root of 2.
What is secant? What over what?
Opposite over adjacent.
That's tangent. What's secant?
Hypotenuse over adjacent.
Hypotenuse over adjacent. So
Square root of 2 over 1.
square root of 2 over 1, or just square root of 2. But we're not done. One last thing we have to think through, and that's ASTC. Quadrant 2 secant is? ASTC. In the second quadrant, secant is? Negative. Because when we see secant, we're thinking cosine, right? We think reciprocal. Cosine would be positive here, so that's where secant's positive, which means it must be negative. In quadrant 2, how many had negative square root of 2 for your first answer? On the next one, we have the sine of 210 degrees. Quentin, quadrant.
3.
Reference angle.
30.
Degrees away from the 180. Sine of 30.
Negative, well, 1/2.
1/2 in ASTC. In quadrant 3, sine is negative. And there we go. How many had negative 1/2? Question. We have the cotangent of 225 degrees. Jamie, quadrant.
3.
Reference angle.
45.
Cotangent of 45.
1.
ASTC, quadrant 3 cotangent is?
Positive.
Positive. For the next one, we have the tangent of 300 degrees. Ethan, quadrant.
4.
Reference angle.
60.
Tangent of 60.
Square root of 3.
Quadrant 4, tangent is?
Negative.
Negative. Square root of 3, our answer. We have the cosecant of 5 pi over 6. Coming back to Chris, comparing the 5 to the 6, remembering 6/6, remembering 12/6. What quadrant?
Second quadrant.
Second quadrant. Reference angle, anytime we see a denominator 6,
Pi over 6.
which is
90.
30 degrees. We got to memorize when we see denominator 6, that's 30 degrees. Cosecant of 30 degrees.
So is it 1 over, or no, it's 2 over 1.
2 over 1, and ASTC quadrant 2 cosecant is?
Positive.
Positive. All right, on the next one, we have the cosine. I'm going to start doing them out loud rather than writing on the board because I'm lazy. Cosine 5 pi over 3, Quentin, quadrant.
4.
4, reference angle.
60.
60, because we have denominator 3. Cosine of 60.
1/2.
1/2. ASTC, quadrant 4, cosine is?
Positive.
So positive 1/2. On the next one, sine of 5 pi over 4, Jamie, quadrant.
3.
Reference angle.
45.
Because anytime we see denominator 4, we know we've got a 45. Sine of 45.
Square root of 2 over 2.
Good. 1 over square root of 2 becomes square root of 2 over 2, but ASTC quadrant 3 sine is?
Negative.
So negative. Square root of 2 over 2. Great job. Ethan, the next one. Quadrant.
4.
3 or 4. I generally say 3. Doesn't really matter, right? It's either 3 or 4. Reference angle?
How 1 over 0 from, I don't know why I put that.
Well, what's the reference angle?
Zero.
Anytime we see denominator 2, halves of pi's are always
Okay, so, square root, 90.
90, right? Reference angle 90. So we're asking ourselves, secant of 90, hypotenuse over adjacent for the 90 is 1 over 0, which is undefined. So it doesn't matter whether it's 3 or 4. Again, it would be positive and 3, or negative and 3, positive and 4, but it doesn't matter because undefined isn't positive or negative, so just undefined for our answer. Coming over here to Chris, 180 degrees, cotangent 180, quadrant.
Quadrant, either 3 or 2 or 3.
2 or 3, we generally say 2, but it really doesn't matter, 2 or 3. Reference angle,
I actually prefer to do 3, so it makes it positive.
it doesn't really matter because,
yeah. So reference angle is 0.
0, because it's 0 away from itself, right?
Undefined.
And cotangent of 0, adjacent over opposite,
So 0, 1 over 0.
we just 1 over 0, which is
Undefined.
undefined, and if it's undefined, then it doesn't matter positive or negative. So back-to-back undefined. Quentin, 150, quadrant.
2,
Reference angle,
30,
30 away from the 180. Tangent of 30,
square root 3 over 3.
square root of 3 over 3, but in quadrant 2, tangent is, so negative square root of 3 over 3. Cosine, 315 degrees. Jamie, quadrant.
4,
Reference angle,
45.
cosine 45.
Square root of 2 over 2.
And in quadrant 4, cosines,
Positive.
so positive, square root of 2 over 2. Ethan, the last one, cosecant 240, quadrant.
3,
Reference angle.
60,
Cosecant of 60 is,
2 times square root of 3 over 3.
yes,
Negative.
and in quadrant 3,
Negative.
negative. So negative 2 square root of 3 over 3. And it went perfect. Wow. All right, questions. We got it? I want some questions.
All right, hold on. Yeah, I'd like to ask a question. Yeah, can you do one on the board?
Well, we're going to do a couple of things together here. I want you to look at page 65 in your textbooks now. Set the handouts aside. Page
Oh, there's not
65
a
in your textbooks.
He did that on purpose.
I did. I'm just evil like that. Page 65 in your textbooks.
You probably were going to have one today, but called it off.
No, we don't have one on the schedule today. We do have a test coming up, though, in 2 more lessons on Friday for you guys. That's lesson 32 on YouTube. Page 65, look at number 8. It gives us the cosine of 11 pi over 4. Now, I already know what reference angle we're going to have, class. It doesn't reduce. It's going to have denominator 4, so I know it's going to be a reference angle of 45 degrees. The question is what quadrant? 11 pi over 4? Thoughts?
Subtract 2 pi.
Subtract 2 pi, but written as
8 pi.
8 pi over 4, right? To get the cosine of
3 pi.
3 pi over 4. Now I know it's in quadrant 2. The cosine of 45 is
square root of 2 over 1.
Yeah. Square root of 2 over 2.
square root of 2 over 2. 1 over square root of 2, square root of 2 over 2. And in quadrant 2, cosine is
Negative.
negative. So even bigger angles, right? What about the negative angle we've got going here? It's sine of negative pi over 6. Well, again, negative angle, you need to add
2 pi.
2 pi, which would be
Pi over 6.
12 pi over 6 to get the sine of
11 pi.
11 pi over 6. Now we can see it's in quadrant 4. And as soon as we saw the 6, we knew the reference angle was going to be 30 degrees. Sine of 30,
So 1 over 2.
1 over 2, and quadrant 4 sines
Negative.
negative. By the way, do you see why I like radians better? It's just automatic with those reference angles. Now, going to some of the other angles, we see on number 12, the cosecant of negative 150 degrees.
Plus 360.
In this case, we have to add 360, which gives us 210 degrees, which is in quadrant
3.
reference angle 30 degrees, cosecant of 30.
Uh, 2 over square root of 3.
Square root of 3 over.
Cosecant of 30.
I'm thinking cosine.
Hypotenuse over opposite.
2 over
2 over 1, yeah, 2 over 1. And quadrant 3 cosecant is negative, so negative 2. What about number 13? The cosine of 495 degrees.
Minus 360.
Minus 360, all right, so it's really the cosine of 135, quadrant,
2.
reference angle,
55. No, 45.
45. Cosine 45?
Square root of 2 over 1. Square root of 2.
Square root of 2 over 2. 1 over square root of 2, right? Adjacent over hypotenuse, which rationalize square root of 2 over 2. Quadrant 2 cosine is negative. So again, even big angles, small angles, again, as long as they come back to one of these special angles in quadrants 1 through 4, we can take exact values of those as well. I want you to do 10, 11, 14, 15. 10, 11, 14, 15. Chris has got it. All right, for sake of time, pencils down. Check your answers here. On number 10, I got negative square root of 3. There in the fourth quadrant. Number 11, I got positive square root of 3. There in the third quadrant. Number 14, I got negative 2. There in the second quadrant. And number 15, I had negative a half in the fourth quadrant. How many got all the ones you did correct? Even if you didn't finish all of them, of the ones you did, you got them right? Questions on any of those 4? All right, no homework this evening. Test coming up Friday over chapters 3 and 4. That'll be in lesson 32. We'll be reviewing tomorrow for your test, and of course test in that next lesson afterward. Have a wonderful rest of your day. You are dismissed.